Okay, greetings students. This is going to be an worked out tutorial of the assignment 1, question 1. So let's see how to solve the problem. The problem is basically we have a mass m connected to another mass 2m through a pulley system. So the masses are connected to the pulley. Little mass is going to go up, the other mass is going to go down, and we have to derive the equation of motion and calculate the natural angular frequency of the system. How do we solve this? Obviously, we'll have to use Newton's equations and then model the system using Newton's equations and then do some manipulations over there. The final answer at the end of the day is omega n is equal to 1/3 square root of k over m. Well, the first step in any problem is to draw a free body diagram and then take it from there. So we have the system over there, and let's do it like this. There is a mass which is pushing down, and the mass has a weight. Let's call the weight W, where W would be the mass times the gravity. The weight is pushing down. There's going to be a tension force in the cable. Let's call the tension T. The tension is going to go through the cable or the rope, so it's going to go around, and then the tension is going to go here, like so. Actually, the direction is wrong. It'll go the other way around. Why would it go the other way around? I'll explain now. So there is a tension, basically a force that is going through the cable and is going in that direction. But the cable itself is not flying out into outer space, so the tension would go also in the opposite direction, like so. Okay, the mass is at an incline to the horizontal at an angle theta. Let's keep things simple. Call the little mass m1 and assume the mass is going up the incline by a displacement x1. The spring constant would be k. That is assumed over there. Okay, what else do we need to do? How do we do this? Okay, so the weight over here is W is equal to the mass times the gravity. We have to assume the mass and friction of the pulley are insignificant, and let's, for the sake of simplicity, assume that the cable or the string is inelastic. In other words, the cable or the string cannot stretch. It has a fixed length, such as a wire cable or rope or something like that. Let's assume the length of the cable from the point of contact over here to more or less where the pulley is a distance or a length of S2. S2 because this is a mass M2 for the sake of argument. That's a mass M1. And this over here is a mass m1 for the sake of argument. In other words, m1 is equal to m, and m2 is equal to 2m. Okay, we keep it like that. So let's say this is m1. Let's not worry about that. And this is M2. Okay, we keep things general like so. What else do we observe about the system? Well, there's a spring at the top. So if the mass moves a distance x1, it is going to create a retarding spring force in this direction of minus k x1. over there. Obviously, we might have to take some components and things like that in order to account for the angle. Okay, so we assume that the mass m1 is going to go along the incline, and we assume the mass m2 will go up in a vertical direction. Okay, what can we do now going further? This is basically your first year mechanics, an extension of your first year mechanics or applied mechanics calculations. So we assume also that the length of the cable is S1 from year to year, and obviously the length of the cable in the same direction is also S1. Now we made the assumption that the length of the cable or the string is going to be constant, and let's assume that the total length is big L for the sake of argument. What does that mean? Well, it means that the length of the cable S2 plus S1 plus S1 is equal to L. Okay, so on the right hand side, the total length of the string or cable is big L. That is equal to the length of the cable on this side from year to year plus the length on the other side. We know that is constant. If that is constant, what can we do with it? This is basically deriving the equations for a pulley. We can take the time derivative of it and then do some additional calculations. So let's take the derivative of this. That's my expression. We'll take the derivative of this. We have the expression. We're taking derivatives of both of them. And if we take the derivative of a displacement, we will have a velocity. So, write down the equation. Why is that 0 on the right hand side? Because this is constant. The length is constant, so we don't need to do anything about that. Now we can take the derivative again and see what happens. Okay, so we have the expression. Take the derivatives again. Derivative of velocity will be an acceleration. So that means that will give us an equation, and at the end of the day, if we assume that the acceleration of the mass m1 is a1, in other words, the mass m1 has a displacement x1, a velocity v1, a velocity, and then an acceleration a1, we can relate the kinematic properties of mass m1 in terms of the properties of m2. We can rearrange the equation, and that equation will basically give us the acceleration a2. Okay, so in this first video, this will give us the kinematic results. Afterwards, we'll take these kinematic results and take it from there further in the analysis. So this is kinematic analysis. What is a kinematic analysis? A kinematic analysis is basically the geometry of the problem and then we use the geometry of the problem to work out the kinetics or the dynamics of the problem. Essentially, the first part of the problem is to draw the picture, do a free body diagram, work out some kinematic relationships, and then afterwards we'll take the kinematic relationships and put it into Newton's equations and then derive the equations of motion. Okay, that is the end of the first part of the video.